Hello friends, welcome to the lecture on solution of non-homogeneous linear system with constant coefficients. Suppose x1t, x2t and so on xnt are n linearly independent solutions of the vector differential equation x dot equal to ax. Now we have already discussed how to find n linearly independent solutions of this homogeneous vector differential equation. So, suppose x1t, x2t and so on xnt are n linearly independent solutions of the vector differential equation x dot equal to ax, then every solution xt of the vector differential equation x dot equal to ax can be written in the form xt equal to c1 into x1t plus c2 into x2t and so on cn into xnt, where c1, c2, cn are constants. Let xt be a matrix whose columns are these n independent solutions x1t, x2t and so on xnt. Then 2 can be written in the concise form xt equal to xt into c. You can write it like this: c capital xt is equal to x1t, x2t and so on xnt. Okay. Now, when you find out xt into the column vector c, what do we get? Xt into c equal to x1 t, x2t, xnt multiplied by the column vector c1, c2, cn. Okay. Now, these x1t, x2t, xnt are themselves column vectors. Okay. So, when you multiply c1, c2, cn, this is n by n matrix. xt is n by n matrix whose first column is x1t, second column is x2t and the last column is xnt. Okay. So, when you multiply this n by n matrix by c1, c2, cn, what you get is xt equal to xt into c. Okay. So, this is xt equal to xt is a column vector. Okay, and it is equal to n by n matrix your xt and multiplied by c vector. Okay. So, this is nothing but this is equal to c1 times x1t plus c2 times x2t and so on cn times xnt. So, it is the general solution of the vector differential equation x dot equal to x. Now, a matrix xt is called a fundamental matrix solution of the vector differential equation x dot equal to x if its columns form a set of n linearly independent solutions of 1. So, xt here which comprises of these n linearly independent solutions x1t, x2t, xnt is a fundamental matrix solution of equation 1. Now, you can write these n vectors in any order. So, there is not a unique fundamental matrix. Any matrix, okay, where the n columns are the n linearly independent solutions of the vector differential equation x dot equal to x will always be called as a fundamental matrix solution of the vector differential equation. So, xt here capital xt is a fundamental matrix. Now, let us consider a vector differential equation x dot equal to ax. Okay. So, A is this 3 by 3 matrix 1 minus 1 4 3 2 minus 1 2 1 minus 1. In order to find the fundamental matrix, in order to find the fundamental matrix of this vector differential equation, what we do is we first find 3 linearly independent solutions of this vector differential equations. So, for this we first write the characteristic equation of the matrix A, determinant A minus lambda equal to 0. It will give you a cubic equation in lambda. So, when you solve that cubic equation in lambda, you will get the values of lambda as 1, 3 and minus 2. You can see the 3 values of lambda are real and distinct, and therefore, the corresponding eigenvectors will be linearly independent. For lambda equal to 1, you can check that for lambda equal to 1, eigenvector is eigenvector for lambda equal to 1 is minus 1 4 1 transpose. Okay. And similarly, eigenvector for lambda equal to 3 will come out to be 1 2 1 transpose, and eigenvector for lambda equal to -2 is -1 1 1 transpose. Okay. Now, we know that if lambda is an eigenvalue of the matrix A and V is the corresponding eigenvector, then e to the power lambda t into B is a solution of the homogeneous vector differential equation x dot equal to x. So, here x1 t equal to e to the power lambda t, that is e to the power t into -141, which is an eigenvector corresponding to lambda equal to 1. This is one solution of the vector differential equation, other solution corresponds to the other eigenvalue and the corresponding eigenvector lambda equal to 3. So, e to the power 3 t, and then you have 1 2 1, and x3 t equal to similarly e to the power -2 t, and then -1 1 1. Okay. These three eigenvectors, these three solutions x1 t, x2 t, x3 t of the vector differential equation are linearly independent, because their values at t equal to 0. x1 0 is -1 4, x2 0 is 1 2 1, x3 0 is -1 1. Okay. The three vectors x1 0, x2 0, x3 0 are linearly independent, because they are eigenvectors corresponding to the distinct eigenvalues 1 3 -2. So, these three vectors are linearly independent, and therefore, x1 t, x2 t, x3 t are linearly independent solutions of the given vector differential equation. Okay. Now, we can write a fundamental matrix. Fundamental matrix x t will be equal to x1 t, let us take first column x1 t, x2 t, x3 t. Okay. Then x1 t, you multiply e to the power t inside. So, minus e to the power t, 4 e to the power t, and e to the power t. So, you get minus e to the power t, 4 e to the power t, and e to the power t. This is first column. Second column similarly e to the power 3 t, 2 e to the power 3 t, and then e to the power 3 t. This is second column, and third column will be here minus e to the power -2 t, e to the power -2 t, and e to the power -2 t. So, this is how we form a fundamental matrix of solution of x dot equal to x. So, x t is this matrix, it is a fundamental matrix solution of the given system. Now, we have seen that e to the power a t, where a is NYN matrix, is given by this series I plus a t, a square t square by 2 factorial, and so on, a to the power n, t to the power n by n factorial. E to the power a t is not easy to compute from this expansion I plus a t plus a square t square by 2 factorial, and so on, but we will see in the theorem which we are going to now state that it can be computed directly from any fundamental matrix solution of the vector differential equation x dot equal to x. The theorem is like this: let x t be a fundamental matrix solution of a differential equation 1, then e to the power a t is x t into x 0 whole inverse. X inverse 0 is what I mean to say the matrix x 0 inverse. Okay. So, x inverse 0 is the inverse of the matrix x 0, that is, when you know the matrix x t, just put t equal to 0 there. So, then x 0 is will be equal to x 1 0, x 2 0, and so on x n 0. So, this matrix n by n matrix you will get, you find the inverse of this x 0 to get this x inverse 0 or x 0 inverse. So, in order to determine the matrix e to the power at, we need to know a fundamental matrix of the vector differential equation and then the inverse of the matrix x 0. Okay. So, the product of the two will then give e to the power at. Now, let us consider a non-homogeneous linear system of differential equation with constant coefficients. So, let us say we consider dx by dt equal to a x t plus f t, where A is a n by n matrix A I j n cross n and f t is a column vector with components x 1 f 1 t, f 2 t and so on f n t. Earlier we considered only homogeneous equations where we took this f t as a 0 vector. Now, after that we have tackled the homogeneous linear systems of differential equations with constant coefficients. Now, let us consider the case of a non-homogeneous linear system of differential equation with constant coefficients. Now, so in order to find the general solution of this equation 4, what we do is we proceed in the following manner. First, we find the general solution which we write as x t equal to x t into c to the homogeneous equation 1. Okay. So, homogeneous equation 1 is what? Dx by dt equal to Ax. Okay. The homogeneous equation corresponding to the non-homogeneous linear system 4 is dx by dt equal to x. So, we find general solution of this, that means we find n linearly independent solutions x 1 t, x 2 t and so on x n t of this homogeneous linear system, and then form the fundamental matrix as we have discussed just now, fundamental matrix x t equal to x 1 t, x 2 t and so on x n t, whose n columns are these n linearly independent solutions of dx by dt equal to x. So, this is fundamental matrix and we then multiply the this x t by c, okay, to get the general solution. So, c into x t, as we have seen earlier, this is nothing but c 1 x 1 t plus c 2 x 2 t and so on c n x n t. So, first we find the n linearly independent solutions of the vector differential equation dx by dt equal to x, and then write the general solution, okay, c 1 x 1 t plus c 2 x 2 t and so on c n x n t, which in a concise form can be written as c into x t. So, we find this homogeneous solution of the general solution of the homogeneous equation x dot equal to x, and then we find a particular solution x p t, we write it as x p t to this non-homogeneous system. Okay. So, then the combination of the two x c t and x p t, okay, will give us the general solution of the non-homogeneous system 4. Okay. Non-homogeneous system 4 will have the general solution given by x t equal to x c t plus x p t. Now, let us see how first we see that it is a solution of the system 4, and then we see that it is a general solution. So, let us first show how it is a solution of 4. Okay. So, let us in the system 4 let us put x t equal to x c t plus x p t. So, this is your dx by dt equal to a x t plus f t, let us put in that. So, we have d over dt, this is our system. So, first we show that x t equal to x c t plus x p t is a solution of this. So, d over dt, let us take the left hand side, let us put for x t x c t plus x p t. Then d over dt of x c t plus x p t, we know this is d over dt of x c t plus d over dt of x p t. Now, x c t is the general solution of the homogeneous system dx by dt equal to a x t. So, we get here d over dt of x c t equal to a x c t plus x p t is a particular solution of this system 4. So, d over dt of x p t will be equal to a x p t plus f t. Now, let us combine, this can be written as a xct plus xpt plus ft, and this will be equal to xct plus xpt is equal to xt. So, we have axt plus ft. So, xt equal to xct plus xpt satisfies the system 4, and therefore, xt is a solution of 4. Now, we see that we know that xt equal to xct plus xpt contains n constants in the solution xct of the homogeneous system. So, this solution xt equal to xct plus xpt contains an arbitrary constant C1, C2, Cn, and therefore, xt is a general solution of this non-homogeneous system dx by dt equal to axt plus ft. Now, when we want to find the general the particular solution of the initial value problem. So, let us consider x dot equal to axt plus ft, where at t naught we assume that xt has the value x naught. Then this this solution for this initial value problem is obtained by calculating the constant vector c that occurs in xct. Okay, we have xt equal to xct, that means xt into c plus xpt. This constant vector c, which is we have taken as c1, c2, cn. So, this constant vector c is calculated by using the value of xt at t equal to t naught. When you put t equal to t naught here, we get x naught equal to x t naught into c plus xp naught, xp t naught. Okay. So, this c is calculated from here, and then we put the value of c in this solution xt equal to xt into c plus xpt to arrive at a particular solution of the initial value problem. Now, the question arises how we find a particular solution of the system 4, okay, of this system. How we find a particular solution. So, we state a formula for this particular solution of system 4. Let xt be a fundamental matrix. So, in order to find a particular solution to the system 4, we need to know the a fundamental matrix of 4. That is, let us recall we have the system dx by dt equal to axt plus ft. So, this theorem tells us a particular solution xpt can be found once you know a fundamental matrix of the homogeneous system dx by dt equal to ax, that is xt equal to x1 t, x2 t and so on xn t. So, if you have a fundamental matrix for the system dx by dt equal to ax, then that fundamental matrix you put here inside the integral. So, you have xt, then you find the inverse of the matrix xt. So, that is xs, s is the variable of integration here. So, inverse of the matrix xt you need to find. Now, remember x1 t, x2 t or xn t are n linearly independent solutions of dx by dt equal to ax. So, xt is a non-singular matrix, and therefore, we can find its inverse. So, we find inverse of this matrix xt and put here the value of xs inverse, and then multiply by fs. This vector ft is known to us, and then integrate with respect to s. So, we shall get the matrix, we will get the solution, particular solution of equation 4. Okay. So, we know xpt, and then we add xct, the general solution of dx by dt equal to axt to that, and have the general solution xt equal to xct plus xpt of the system 4. So, let us see how we do go about it. Let us take an example x dot equal to ax plus ft. So, A here is this matrix 6 by 7 minus 15 by 14 and then minus 5 by 7, and we have 37 by 14. This is matrix A, and ft is equal to the vector e to the power 2t, e to the power minus t. Now, we have an initial value problem. So, we are given that when t naught equal to 0, x t naught is x naught, that is the vector 4 minus 1. So, we have x 0 equal to 4 minus 1. So, first we will find the general solution of the non-homogeneous system x dot equal to a x plus f t, and then use the initial condition x 0 equal to 4 minus 1 to arrive at the solution of this initial value problem. Now, it is easy to see that determinant of a minus lambda equal to 0 gives us lambda equal to half and lambda equal to 3. So, let us take lambda 1 equal to half, lambda 2 equal to 3. So, we get the two eigenvalues which are real and distinct. Okay. So, the eigenvalues are real and distinct. We can find eigenvectors corresponding to lambda 1 equal to half and lambda 2 equal to 3. Since the eigenvalues are real and distinct, the corresponding eigenvectors are orthogonal. So, b 1 and b 2 we can find they are orthogonal, they are linearly independent. Okay. Now, what we have x t equal to, x t is a fundamental matrix. So, x t equal to now x 1 t, x 2 t. So, these eigenvalues are real and distinct. So, x 1 t will be e to the power lambda 1 t, that is e to the power half t into 3 minus 1, 3 1 sorry 3 1, this one x 1 t, and x 2 t will be e to the power 3 t e to power lambda 2 t into b 2. So, minus 1 2, and you can see this will be equal to 3 e to the power half t e to the power half t e to the minus e to the power 3 t and 2 e to the power 3 t. So, we get this fundamental matrix. Okay. Now, what we do, once we have x t with us, fundamental matrix with us, we can write x c t. So, x c t is equal to x t into c, where x t is x t is 3 e to the power t by 2 e to the power t by 2, and the second column is this one, what is that, minus e to the power 3 t 2 e to the power 3 t multiplied by the vector c 1 c 2. Okay. So, when you multiply this column vector to this 2 by 2 matrix, you get 3 c 1 e to the power t by 2 minus c 2 e to the power 3 t. This one first element, and second element is c 1 e to the power t by 2 and then 2 c 2 e to the power 3 t. So, we get this general solution of the vector equation x dot equal to a x. Now, let us find a particular solution of x dot plus a x, x dot equal to a x plus f t. So, particular solution by our theorem is given by x t into x s inverse into f s. Now, x t we know, this is our x t, this is our x t. We can find its determinant. Okay. Since the vectors x 1 t and x 2 t are linearly independent, this matrix its determinant is non-zero. Okay. So, we can find determinant of this matrix x t, we can find adjoint of the matrix x t and then find x t inverse. So, x t inverse is adjoint of the matrix x t divided by determinant of x t. Now, when you do this, you will get this matrix x t inverse equal to 2 by 7 e to power minus t by 2, 1 by 7 e to power minus t by 2, minus 1 by 7 e to power 3 t, 3 by 7 e to the power 3 t, and hence you now you put this x t inverse here in this. Okay. So, you have x t with you, this is x t, then x s inverse, when x s inverse will be 2 by 7 e to the power minus s by 2, 1 by 7 e to power minus s by 2, minus 1 by 7 e to the power 3 s, 3 by 7 e to the power 3 s. So, put here, and f s is given to us as e to the power 2 s e to the power minus s. So, we put the value of f s inside this. then we have to integrate with respect to s. Remember, this t and s are independent variables. So, x t you can even write outside the integral. Okay? We just need to find the product of x s inverse and f s and then integrate with respect to s, and then multiply ultimately by the x t matrix, that is the fundamental matrix, this one. So, after these computations, what you get is x p t equal to this matrix 1 by 7, 3 e to power 2 t, minus 5 by 5 by 4 e to power minus t, 10 by 3 e to power 2 t, minus 13 by 6 e to the power minus t. And so, we can write a general solution x t equal to x c t plus x p t, x t equal to x c t plus x p t gives us. Now, let us see x c t is what? This is 3 c 1 e to the power t by 2 minus c 2 e to power 3 t, and then we have c 1 e to the power t by 2 plus 2 c 2 e to power 3 t, and to this we add this matrix 3 by 7 e to the power 2 t, then we have 3 by 7, then we have 10 by 21, 10 by 21 e to the power 2 t, and then we have minus 5 by 28 e to the power minus t, and then we have minus 13 by 42 e to the power minus t. Okay, so, we add the two matrices, है ना? Yeah, we add the two matrices x c t. Okay, x c t is this and x p t is this, x p t. Okay. So, this is, oh sorry, this is like this. Okay. So, we get then 3 c 1 e to the power t by 2 minus c 2 e to the power 3 t plus 3 by 7, we add component wise, e to the power 2 t minus 5 by 28 e to the power minus t, and then 3 c 1 e to the power t by 2 plus 2 c 2 e to the power 3 t, and then we get 10 by 21 e to the power 2 t, and then minus 13 by 42 e to the power minus t. So, this is a general solution of x t equal dx by dt equal to a x plus f t. This is general solution of this. Now, let us apply the initial condition. So, we put x t equal to 0 in this, and so x 0 will be equal to, put t equal to 0 here, 3 c 1 minus c 2 plus 3 by 7 minus 5 by 28, and here we get c 1 plus 2 c 2 and 10 by 21, and we get minus 13 by 42. This is equal to we are given 4 minus 1. So, this will give you two equations, 3 c 1 minus c 2 plus 3 by 7 minus 5 by 28 equal to 4, c 1 plus 2 c 2 plus 10 by 21 minus 13 by 42 equal to minus 1. So, these are two linear equations in two unknowns c 1 and c 2. We can determine the value of c 1 and c 2 here, and then put in the general solution. Okay. So, c 1 and c 2 we can put here, and when you put the values of c 1 and c 2, you arrive at this solution. So, x t equal to 19 by 7 e to the power. So, you can see here the coefficient of e to power t by 2 is 19 by 7. That means 3 c 1 equal to 19 by 7. So, c 1 will come out to be 19 by 21 when you find c 1 equal to this, and the coefficient of e to power 3 t is minus c 2 is 29 by 28. So, c 2 will come out to be minus 29 by 28. So, put these values, okay, of c 1 and c 2 here in this general solution, you get the solution of the initial value problem. Now, the solution formula for the non-homogeneous system. Okay, the solution formula for the non-homogeneous system, x dot equal to Ax plus Ft. Using the fundamental matrix we know is given by this. Okay. Now, let us apply, we will find the another formula, alternate formula for the matrix solution. E to the power at, we know e to the power at is x t into x inverse 0. So, if you put here the value of x t, we get this following, x t equal to, we can find this formula, c, then x t is equal to x t, if you can multiply by post multiply by x 0. So, e to the power a t into x 0, this is equal to x t. So, we will get the value of x t here. So, e to the power a t into x 0 plus integral x t is equal to e to the power a t into x 0. Okay. Xs inverse, xs will be e to the power as equal to xs into x inverse 0. Now, we want to find xs inverse. So, pre multiply by xs inverse. So, xs inverse e to the power as equal to x inverse 0. Okay. And xs inverse is therefore equal to e to the power b multiply post multiply by e to the power minus as. So, we get x inverse 0 e to the power minus as. So, let us put here. So, x inverse 0 into e to the power minus as fs ds, and we arrive at now c into x 0, x 0 is a constant, c is a constant. So, we can put another constant c dash e to the power a t plus x 0 into x inverse 0 is identity matrix. So, e to the power a t, e to the power a t into e to the power minus a s is e to the power a times t minus s into fs ds. Okay. So, this is the formula, and when you have to use x t naught equal to x naught, then you to determine this c dash, okay, what you do, put here that value. So, x t naught is equal to x naught equal to c dash e to the power a t naught, and here you get the integral, okay, t naught to t. Okay, sorry. So, we will have okay, c x okay, x naught, when we put t equal to t naught, okay, yeah, this integral will be 0. So, x t equal to x naught equal to c dash a t naught, and therefore, c dash equal to x naught into e to the power minus a t naught. So, you put here c dash equal to x naught into e to the power minus a t naught. So, we will get e to the power a times t minus t naught into x naught plus this integral. You can put here t equal to t naught, this integral vanishes, and what we get is x t naught equal to x naught. Now, this formula we can also use to determine the solution of example 1, okay, particular solution of example 1. Here we need to find the matrix e to the power a t. E to the power a t can then be found by x t into x inverse 0. Now, to determine x inverse 0, what you do? You have the matrix x t with you, put t equal to 0 in that, you will have x 0, 3 by 3 matrix x 0, find the inverse of that matrix, you will have x inverse 0. So, then we will take the product of x t with x inverse 0 to determine e to the power a t, and put here in this formula, we will get the solution. Now, there is one more method, solution method by decoupling. If A is diagonalizable, we can we know that there exists a non-singular matrix P such that A equal to P d P inverse, and then the system 4, okay, dx by dt equal to Ax plus Ft can be expressed like this. If you assume x t equal to p u t, suppose you assume x t equal to p u t, then dx by dt, where p is this matrix. So, p du by dt. So, what you get? P du by dt equal to A is p d p inverse into x is p u t plus f t. Okay. So, p du by dt is equal to Now, P inverse P is identity matrix. So, you get PD UT plus FT. Now, pre-multiply this equation by P inverse. So, P inverse P will be identity matrix and we will get du by dt equal to dut plus P inverse Ft. So, this is how we get this formula. Okay. So, if the matrix A is diagonalizable, okay, then we can use this formula also. We will solve this equation. We know the matrix P. P is the matrix which is found from the eigenvectors of A. Okay. So, we find the matrix P from the eigenvectors of A. Let us say they are B1, B2, Bn. Since they are linearly independent, we will be able to find P inverse also. Okay. D matrix will be corresponding, suppose B1 eigenvector corresponding to lambda 1, B2 eigenvector corresponding to lambda 2 and Bn eigenvector corresponding to lambda n, then this is your D matrix. Okay. So, we have A equal to PD P inverse. So, we know the D matrix, we know the matrix P inverse, because we know P, we can substitute in this and determine solve this equation. Okay. Let us see for example 1. In the case of example 1, we have seen the eigenvectors corresponding to lambda equal to half and 3 are 3 1 and minus 1 2. So, this is your P matrix. D matrix is lambda 1 equal to half, D 2 equal lambda 2 equal to 3. So, this is D matrix. X t equal to P u t, let us assume. So, then du by dt equal to d u t plus P inverse F t. P inverse, if you find for this matrix P, it comes out to be this matrix 2 by 7, 1 by 7, minus 1 by 7 and 3 by 7. Okay. So, we know the matrix D now. Okay. We know the matrix P inverse, and so we can find P inverse into Ft. Ft is also known to us. Okay. Now, so when you, so now what will happen, du by dt is, let us say ut equal to u1 t u2 t. Okay. So, this is then du by dt will be du1 by dt or du2 by dt. This is du by dt. D is your matrix 1 by 2 0 and 0 3. Okay. u2 is u is u1 t u2 t. Then you know P inverse into Ft, which is again a column matrix. Okay. So, you will have du1 by dt equal to, you can multiply here half u1 t plus, let us say P inverse Ft is alpha t beta t. So, you will get plus alpha t, this is one equation, and the similarly second equation is du by dt equal to 3 u2 t plus beta t. Now, this equation and this equation, they are linear equations in u1. Okay. We know how to solve the equation dy by dx plus py equal to q, where p and q are functions of x. So, you can solve du1 by dt minus half u1 equal to alpha t from this, and dut by dt minus 3 ut equal to beta t also from this. We can find the integrating factor and then find the solution u1 t and u2 t. So, we will find that. So, so these are the equations for u1 and u2 differential equations. When you solve them, you get the values of u1 t and u2 t, and then you apply this initial condition. Initial condition, we have assumed that x t equal to put. So, x 0 equal to pu 0, and then u 0 equal to p inverse x 0. P inverse x 0 if you find, okay, you will get 1 minus 1. So, u1 0 equal to 1 and u2 0 equal to minus 1. So, we have these two linear equations in u1 and u2 with the initial conditions u1 0 equal to 1, u2 0 equal to minus 1. We can solve them easily to get the value of u1 t and u2 t. Now, we know the vector ut, so x t will be p into ut. Okay. So, multiply this vector ut whose components are u1 t and u2 t by the matrix P, we will get the solution of the example 1. So, this is another method where which we use in case the matrix A is diagonalizable. So, with that I come to the end of my lecture. Thank you very much for your attention.